Practical Web Cache Poisoning, Redefining Unexploitable. James Kettle mostrará cómo comprometer distintos tipos de sitios web y frameworks usando Esoteric Web Futures para convertir el caché de estas en sistemas de distribución de exploits.
Hi, good evening and welcome to Practical Web Cache Poisoning. Have you ever been working away and just noticed something that wasn't quite right and thought, that's weird, but I think I'll deal with that later on when I have more free time? For years, web cache poisoning has been a vulnerability that people didn't want to think about. It's existed mostly as one of these kind of theoretical things, often used to scare people into deploying patches, but rarely actually proven to exist. And for years, I lived in fear of web cache poisoning and its notorious complexity. But earlier this year, I found myself in a situation where I had no choice but to try it and discover that actually, web cache poisoning is wonderful. So today, in this session, I'm going to share with you practical tools and techniques to detect, explore, and exploit web cache poisoning. If you ever publish research yourself, you'll know that often, as soon as you do, someone will find something kind of similar done by someone else about 5 years earlier, and then they'll accuse you of copying it. And there's no better illustration of this than the history of header-based web cache poisoning. In 2013, I wrote a blog post called Practical HTTP Host Header Attacks, and I demonstrated using cache poisoning on Joomla with the host header. And I felt really quite pleased with myself about this until someone else pointed out the idea was suggested by someone else in 2008. The thing was, the original post from 2008 didn't provide a proof of concept, and as a result, it was pretty much ignored by the entire security community. So moving on, is my mic? So moving on, last month I published Practical Web Cache Poisoning, and that was fine and wonderful, and then one of my victims pointed out that for the last year there's been a public entry in the Rails bug tracker that just says everything built on Rails is vulnerable to web cache poisoning, and maybe we should fix that. And that had just sat there publicly where anyone could see it for the whole of the last year. I had no idea. And this mic is not great. And reading that, I noticed a link to a report on HackerOne. Back in 2014, someone found that www.hackerone.com was vulnerable to web cache poisoning. They called the report DNS cache poisoning, and it was a bit confused. But ultimately, they had successfully found a real vulnerability on that site, but no one had really understood what was going on. So the end result is, ultimately, depending on your perspective, this research is either hot new research into a cool new technique for taking attacks to new levels, or it's just some fresh insight into an old, tangled mess of stuff that's been overlooked and forgotten for years. Either way, I hope you'll enjoy it. So first, I'm going to talk about what web cache poisoning is and how you can find it. Then I'll have a look at a bunch of real examples on various websites that I was able to exploit. And then I'll talk about how not to get your cache poisoned and have an all-new section on how people fail to not get their cache poisoned. And then I'll wrap up and take 5 minutes of questions. So first of all, a bit of context. Practical web cache poisoning, this presentation is not about poisoning browser caches. Browser caches these are client-side caches, and they're just not that exciting from a cache poisoning point of view. Also, there's a technique that was unveiled last year called web cache deception. So it has a similar name, but it's ultimately quite a different attack. Web cache deception is about tricking caches into saving sensitive information belonging to other users, whereas web cache poisoning is about putting malicious code in caches so that you can exploit users. So I'm not going to be talking about web cache deception. More sellotape. Excellent.
There we go.
Thank you. Cool. Cheers. Also, it's possible to poison caches using response splitting and request smuggling sometimes, but those techniques have their limitations, and I'm not talking about those either. And finally, and most importantly, practical web cache poisoning is not theoretical. Every single example in this presentation is taken from a real system that I was able to successfully exploit with this technique. Now, first, let's take a look at how caching is supposed to work. Here we've got 3 users fetching the same resource, one after the other. This resource could be an image or some CSS or even just a HTML page. And when the cache sees the first user fetching this resource, it saves a local copy of it. So when the next 2 users try and fetch it, the cache can just serve up its local copy, and it doesn't need to talk with the backend website, which makes things faster and reduces load on the backend side. And the objective of any kind of web cache poisoning is to send a request to the backend website that results in a harmful response coming back to us, and then we want the cache to save that response and serve it up to other users. So we want to turn the cache into an exploit delivery system. The first step to achieving this is to ask the question, how does the cache know that those first 3 users are fetching the same image? It can't just be doing a byte-by-byte comparison on the requests they're sending, because HTTP requests are full of all kinds of junk. For example, if those users had different browsers, then the user agent header would be different and the caching wouldn't work. To deal with this, caches have the concept of cache keys. They say we only care about certain parts of the request. Generally, just the host header and the request line. And if a value that's not in the cache key changes, the cache basically ignores that entirely. And that mostly works, but it sets us up for the next question, which is, what happens if something important is not included in the cache key? This is where things start to get interesting. For example, here we've got 2 requests, both trying to fetch the same white paper. So the URL is the same. But one of them is using this language cookie to fetch it in English, and the other one is fetching it in Spanish. And that system will work absolutely fine until you put a cache in front of this site. As soon as you do that, things will go wrong because the cookie header won't be in the cache key. So when the cache sees someone fetching the white paper in English, it will go great and it will save it. And then if someone tries to fetch it in Spanish, they'll end up with the English version. And obviously, this is just a harmless nuisance, but this is the behavior that we're going to try to turn to our advantage. In effect, everything that's not in the cache key is part of the cache poisoning attack surface. So, how do we find cache poisoning? Well, the first step is to find some input that's not included in the cache key. Generally, that means a HTTP header or a cookie. And to help you do that, I've released a free open source tool called Param Miner, which will just do this step for you automatically, trying tons and tons of different header and cookie names and seeing what works. Once you've done that, the next step is to figure out what you can do with this input. Because if all you can do is change the language of the page, well, that's not very exciting. But often we can do cooler stuff. When you're doing these 2 steps, it's extremely important to specify a random cache buster on all your requests. If you don't do this, you might get a response from the cache rather than getting a response from the backend server. And when that happens, any unkeyed inputs you've specified are effectively completely invisible. I think this property is the reason why cache poisoning has remained so low profile for so long, even though once you understand this, it's not actually very difficult most of the time. So once you've found your input and you've found something reasonably harmful you can do with it, the next step is just to try to get the cache to save it and serve it up to other users. And often, this involves no effort whatsoever. You'll find that the cache has already saved it. But if the cache doesn't seem to want to save it, then you'll need to reverse engineer the cache a teeny bit to figure out what kind of rules it's using to decide what it should and shouldn't save. For example, some caches will be set up to only save resources that have certain file extensions, like JPEG, say. Or other ones may not save things with certain headers or certain content types, and so on. So you'll need to reverse engineer these rules and then just browse the website to see if you can find a page that complies with these rules, will get saved in the cache, and can be poisoned. And that is pretty much all the theory. So now, let's take a look at what happens when we apply this theory to real websites. Now, part of the goal of this section is that I just want to show you that cache poisoning really works. But I've chosen these specific examples out of the many, many vulnerable systems that I found to show you some of the challenges that you might run into and give you some ideas as to how to deal with them. One point that I just want to make right now is that these examples affect targets using all of these different caches. Ultimately, this is a technique that works on any cache. It's not specific to a given vendor. So, to begin with, we'll have a nice, easy example. We'll look at redhat.com. Here, if you look at the response, it doesn't look very promising, right? It has this cache control, no cache header that says don't cache this response. And also, there's no evidence from this that they even are using a cache. But headers will lie to you. So what I would say is just pretend you know there's a cache and then worry about whether stuff's actually getting cached later on. So we're just going to take this and we're going to run a param miner and tell it to guess headers. And when we do that, param miner will find that the X-forwarded host header is reflected in this particular bit of HTML in the page. So we've just done step one and we've found our unkeyed input. The next step is to see what we can do with this input. And well, what's the most obvious attack to try with this header? It's cross-site scripting, right? We can break out of this input and inject some malicious JavaScript into the response. And okay, that's cool, but by itself, this is useless. We need to get the cache to serve this up to our victims. And so what we're going to do is just test and see whether this harmful response has been saved in the cache. So we're going to send a request to it without any special headers. We're basically simulating a normal user visiting that URL. And if we do that, sure enough, our injected JavaScript comes back. So we just got full control over the homepage of redhat.com, and it wasn't really very difficult. The only thing that I need to mention here is this safe equals 1 parameter that you can see highlighted in blue. This is not part of Red Hat's website. This is something that I've manually specified, because if I don't specify this, there's a risk that I will poison their genuine homepage, and tens of thousands of people will get alert boxes popping up and will not be very happy. So it's worth always bearing in mind that you need to specify some kind of cache buster like this to ensure that you're poisoning something that only you are going to see. Now, headers will lie to you, but they will also tell you useful things. So let's pretend you're a more malicious person and you want to poison the real version of a home page, so you don't want to use this cache buster. That effectively means that you're in a race with all the legitimate users of that website, because you need your request to be the first one to hit the site after the current cache entry for their homepage expires. And headers will sometimes help you out with that. So here on unity3d.com, we can see we can inject using xhost, blah, blah, blah. But the interesting thing is these age and max age headers. Taken together, those tell us the exact second that this current cache entry will expire. So they tell us the exact second that we need to start spamming our payload at this server in order to take control over their site. Headers can give you other clues too. So here on this website, which I can't name, unfortunately, they're specifying the vary user agent header in the response. Vary is an instruction to the cache to add a certain header into the cache key. A word of caution is some caches will ignore this header completely, so don't assume that because something is specified in vary, it's definitely in the cache key, but in this case, it actually is. And what that means is this payload will poison their homepage, but it will only poison it for other people who are using Firefox 60. And that's both a blessing and a curse. It means it's a bit of a headache because if I want to poison the majority of visitors to a website, I need to send this payload over and over with every conceivable user agent. But on the other hand, it's quite handy because it gives me the ability to be slightly more creative. For example, perhaps I happen to know that the development team for this website tends to use Microsoft Edge. Well, that means I can then go, okay, I'm going to poison the site for everyone who's not using Microsoft Edge. And the developers are going to have a really hard time figuring out what's going on. So, at this point, we've seen 3 different websites, and the actual injection has always just been done using boring old reflected cross-site scripting. But life is not always that easy. So here, on this US government website, I found we can control this data site root attribute. And we can't just break out of this and get cross-site scripting because they're encoding it. So we need to look at what this attribute is actually for. And to try and find out, I set up a header injection rule in burp, and then I just manually browsed this website. And what I found was, when I loaded certain pages on this site, my web browser made a request to my server, thanks to this header injection rule, trying to fetch some kind of internationalization data. So let's take a look at what this internationalization data is meant to look like. It's meant to have a mapping of English phrases into the same phrase in a different language. And then this translated phrase is then just concatenated into the DOM by some JavaScript. And so what I found I could do with this cache poisoning is the first step is I would use that header to make everyone fetch their internationalization data from my website. And then on my website, I'd tell their browser to translate English phrases into exploits. And the end result was that if anyone loaded a page containing one of those phrases, they would get exploited. This is quite a common pattern, actually. So you'll often find you can somehow hijack a JSON request and serve up some malicious JSON that's expected to be trusted and can therefore be used to get cross-site scripting. Now, after that exploit, I completely forgot to delete the header injection match and replace rule in burp. And so burp just kept injecting this header into all of my traffic. And I had no idea about this until a few days later when I was just tidying some stuff up. A really weird request had hit my server. This request didn't look like it had come from data.gov. In fact, thanks to this origin null header, which was fully lowercase, which is bizarre, it didn't even look like it had come from a website. And after some investigation, I found that it came from Firefox itself, from a core Firefox feature. Firefox has this feature called Mozilla Shield, and it's on by default, and it's a system for forcibly and silently installing extensions in the background for research and marketing purposes. You may have heard of this because last year they installed a Mr. Robot extension on tens of millions of users, and some people got upset and it caused some headlines. So the way this system works is when you open up Firefox and then periodically, it sends a request to this URL to try and fetch a list of URLs. And one of those URLs, the recipe signed one, points to a list of recipes which define what extensions should be installed. And so Firefox had tried to fetch this. My burp injection rule had added this exported host header, and that had overridden the URLs that the server gave back. And Well, this looked like it could potentially be quite serious because this could get cached. This was being cached. And that meant that I could make every Firefox installation on the planet connect to my system for a list of what extensions to install. Now, unfortunately for me, Mozilla were smart enough to sign these recipes. So I couldn't just make some kind of backdoor extension and then install that on everyone. But what I could do was replay old recipes. So I could audit all their hundreds of old recipes, find one that installed an extension that has now got a known vulnerability, and then effectively force that vulnerability on every Firefox installation worldwide. Also, there was an unsigned version of this recipe list. And apparently Firefox doesn't use the unsigned version, but some of Mozilla's back-end infrastructure for making these recipes in the first place uses that unsigned list. So potentially, I could have compromised that back-end system and maybe with a bit of luck got hold of the signing key and then got a 50 million computer botnet, which would have been fun. Needless to say, Mozilla patched this one extremely quickly when I reported it. Now, some systems don't just use headers to generate URLs, they go beyond that and they use them for internal routing. So here, goodhire.com is using HubSpot. And HubSpot is trusting the exported server header to specify which of your clients they are. And once again, our input's reflected, but it's encoded. We can't just get cross-site scripting that way. But what we can do is I can register myself with HubSpot. And they let me put whatever content I like on my HubSpot site, and then I can use the X-forwarded host header with waf.party, which is my site, and basically trick HubSpot into serving that up on goodhire.com, where it will then get cached by Cloudflare and served up to everybody else. So using this technique, I could effectively take full control over every page on every site hosted with HubSpot. When I initially reported this, I reported it to Goodhire because they had a paying bug bounty program, and there was a bit of a miscommunication, and the end result was that HubSpot just IP banned my office permanently. But this has now been smoothed over, so we're on speaking terms again. Right, this one is my second favorite attack, partly because I'm exploiting a security company, Cloudflare, because they used their own security product on their website. So blog.cloudflare.com is hosted by Ghost, and they are obviously doing something with the X-forwarded host header, because when you specify this header, you get a redirect to /fail. So it looks very much like that HubSpot scenario. But if we try the technique that worked on HubSpot, it doesn't work. We get the correct response after a mysterious 10-second timeout. What we can do, though, is when we sign up with Ghost, they give us a subdomain in case we haven't configured our own custom domain. And if we configure our custom domain, but then specify the subdomain, they do a redirect. And you could trigger that with the X-forwarded host header. So using this, I could replace any response on Cloudflare's blog with a redirect to my site. The only thing was I had to get this cached. And their site was set up to only cache things with certain file extensions. So I could redirect images and just inject whatever into whatever blog posts they've done, which is kind of funny but not very useful. What I really wanted to do was hijack some JavaScript, but I ran into a significant problem there, which is this redirect was being issued using HTTP rather than HTTPS. And that meant that on all major web browsers, their mixed content protection would kick in and block the redirect, and my attack would completely fail. So I was really close to having a really nice exploit, but just couldn't get it to work. And I spent ages trying to find ways around this problem, and I was even considering just contacting Ghost, filing a support request, and saying, please, can you upgrade this redirect to HTTPS? I'll be very happy if you do this. But there were some minor ethical issues with that plan. So instead, I decided to crowdsource a solution. I built a replica of this problem, and I stuck it in my online hacking game. And I said, look, I've made this mission. There's no known solution, but if you do solve it, I'll split the bounty with you, and you'll get fame. And that led to a great community response and 2 awesome solutions. The first one was that in Safari, if the website you're redirecting to is in Safari's strict transport security cache, the redirect gets upgraded to HTTPS before the mixed content block happens. So in effect, it works. After that, Sam Thomas found that on Internet Explorer, you can just issue a 302 redirect over HTTP to HTTPS, and somehow that completely bypasses Edge's mixed content protection. That one's actually a vulnerability in Edge, but whatever. So the end result of all of this work is that if anyone went to Cloudflare's blog in Edge or Safari, I could get full control and execute JavaScript. And if you went there in a different browser, well, I could still hijack images and have some fun with that. Now, things are starting to get a bit more difficult and a bit more complex. On this site, the exported host header can be used to control this property. We can't break out and get direct JavaScript execution, so we need to figure out what it's for. OGURL stands for Open Graph URL, and that's a protocol by Facebook for specifying what happens when a page is liked. So what happens when someone presses like on your page, or when someone just shares a link to your page on Facebook or Twitter or wherever. And so using the exported host header to control this URL, I could effectively take complete control over what happened when someone liked this site. In order to get it cached, I had to specify this session ID cookie, but even having done that, for some reason, the like hijacking wasn't working. And it turned out this target used a whole lot of different caches, and Facebook was hitting a different cache than the one that I was poisoning. So I did some investigation, and I found out that Facebook were touching the cache in Atlanta. So I Googled for cheap VPSs in Atlanta, and I got one that was very cheap, and I used that to do the poisoning. And once I did that, that successfully poisoned what Facebook saw. So here's a quick video. I had to redact it quite heavily, sorry about that. But they go to the web page, they press share, and the end result is they end up sharing whatever I want. The part of the cool thing about this is that Facebook caches that page themselves. So even if the target fixes that vulnerability, they then have to clear Cloudflare's cache. But even then, this page is still poisoned, and anyone who tries to like it will end up liking my content until Facebook's cache is cleared as well. Now, that was great, but hiring a VPS every time that we want to poison a specific cache is a bit of a headache, especially with Cloudflare, because they have a lot of caches. So I thought I'd investigate and see if you can just target specific caches from an arbitrary location. Cloudflare have this great feature. On every Cloudflare hosted site, you can access cdn CGI/trace, and you'll get a bit of meta information about your request, including this colo line, which tells you the location of the cache that you've hit. And so I wrote a simple bash one-liner to send a request to this trace URL on my target website, but to try and send it to every single IPv4 address that's owned by Cloudflare. And the end result was that gave me a mapping of which IP address I should send my payload to poison which global cache. So basically, as long as you're willing to do a bit of recon on the specific target, then you don't actually need to bother using a new VPS every time you want to poison their specific cache. Now, when I first did this research, I got flooded with unkeyed inputs, and I just focused on the most dangerous looking ones, like x-forwarded host. But more recently, I found that some really quite innocent headers can also be quite dangerous. I found this out almost by accident. So I made a cache poisoning challenge in my game just so people could practice with it and learn a bit about cache poisoning. And someone came up with a completely unexpected solution. So first of all, they found that my server, unbeknown to me, supported the X-forwarded proto header. And then they found that although this header is only meant to let you control the protocol, which is pretty boring, actually you can just put a full URL in that header, and it effectively overrides the URL that my game thinks you're trying to access. So this pattern of a header that's meant to do something really basic, and in the basic case, maybe you can use it for a denial of service. But other times, you'll find that with a bit more work, you can escalate and do something much cooler. Now, other times, you'll find headers that look completely useful on their own, but when you combine them with other headers, they'll suddenly become useful. So here, X-forwarded host is only changing the domain attribute in the setCookie header, which is boring. And here, the X-forwarded scheme header on the same server just triggers a redirect to HTTPS, which is also pretty much useless. But if we combine them, then we can turn it into a redirect to an arbitrary URL of our choice. So using this, we can redirect post requests to steal cross-site request forgery tokens, and also, once again, hijack Java JSON load requests and get DOM-based XSS, much like we did on data.gov. Now, the examples you've seen so far, and all of those headers you can see down the right, were all found by Param Miner using inputs from various sources and also basic permutations of those inputs. The one source that I haven't got hold of so far is headers from real live traffic on a heavy traffic website, because no one wants to give me this data. But I'm sure I'll find it sooner or later. Some of these headers, if you look at them, are really quite weird. Things like, for example, path info is an environment variable. You shouldn't be able to set that via a header. Set cookie is meant to be a response header, not a request header. And referrer is spelt differently from the normal referrer header. But I've saved my favorite header until last. I'd like to introduce you to the X original URL header and its partner X rewrite URL, which does exactly the same thing. This header overwrites the path that you're trying to access on the server. So even by itself, it's quite useful. For example, on Unity's website, they've got a front-end proxy that blocks access to /admin. But this proxy isn't aware of that header, so if you can put anything you like in the request line, the proxy will let it through, and then you can put a /admin in X original URL, and that takes precedence, and you get access to the admin page. Now, the reason this header is so cool is because it's supported on so many systems. I initially found it because some of my targets are using Drupal 8. But when I reported this to Drupal 8, the developer was like, what is this header? I've never seen it. I can't even find it in our code base. And it turned out Drupal supported this header because it came from Symfony, which Drupal 8 is built on. And then it turned out Symfony only has this header because it came from Zend. And Zend is a pretty big framework, and basically if you're using a PHP framework, it might well be built on Zend or Symfony. And as a result, these headers work on tons and tons of systems. So let's have a look at what we can do with them. If the site is using an external cache, like every site that we've looked at so far, you can have some fun with the path. You can replace the response to any path with the response to any other path. For example, after sending this request, if someone tries to fetch the Unity for Education page, they land on the Unity for Gambling page, which looks like this. You know, that's an entertaining example, but you can do much more harmful things with this. For example, you could swap the change password page with the logout page, so no one can change their password. But to really prove how dangerous this header is, I need a case study. And for that case study, I'm going to try and target vanilla Drupal, just normal Drupal. Now, Drupal also has a built-in internal cache, which is turned on by default. And this cache is aware of the X original URL header. So it shouldn't make any difference to anything. But my colleague Gareth Hayes noticed there was a kind of a bug in the way their internal cache handles this header. Their internal cache doesn't realize the query string in this header is ignored. So that means on a Drupal site that's not using a normal cache, that just has the internal one, we can't do anything with the path, but we can swap the query string for a different query string, which is really quite powerful. So with this example, if you do a search for kittens, you'll get search results for snuff. But obviously with the query string, you can inject payloads in there and have quite a lot more fun. But for generic mass Drupal exploitation, we need one more ingredient, and luckily, Drupal provides it. So Drupal has this insane feature. If you load any site that gives a redirect as the response, you can specify a destination parameter, and that will override the redirect location. Now, they try and filter this to make sure that it is a same origin redirect, but obviously that's fairly easy to bypass. And yeah, that's it. By itself, this is rubbish, right? It's just an open redirect. But this is the final ingredient that we need to have some fun with cache poisoning on Drupal sites. On business.pinterest.com, they use Drupal. And on certain pages, they import some JavaScript via a redirect. And, well, that's fine. But we can use our internal cache poison to inject this destination parameter when they try to import this JavaScript. And that means they end up importing JavaScript from my website, and I get full control over their browser on that site. So that's just poisoning their internal cache, and it's kind of fun, but it's reliant on the fact that they're importing JavaScript via a redirect. What we really want to do is hijack arbitrary responses. Now, in every example I've shown you so far, we've poisoned the web cache in order to exploit the end user. But Drupal is generally used with two caches. We've got the internal cache, and we've got another cache, most often Varnish, because if you don't have this extra cache, then Drupal will just collapse as soon as it gets some traffic. So what we can do is poison the internal cache in order to poison the external cache. So first of all, we can just find a redirect anywhere on the website. It doesn't matter what URL that's on, and poison the internal cache to convert that into a redirect to our site. And then we can send a follow-up request, which effectively shifts that poison into the external cache at a URL of our choice. So the end result of sending these two requests is that when someone goes to store.unity.com and clicks download installer, they end up fetching malware.exe from my website. I'd like to say Unity handled this really well, and thanks to them for letting me talk about this issue, but ultimately this is really quite bad, and I talked to Drupal and they patched this with a coordinated security release, and also if you update Zend and Symfony, they will remove support for those headers. But there's so many frameworks out there built on these frameworks that currently these headers are still really widely supported. So how do you prevent cache poisoning? Well, one way to do it is not to use caching. That's pretty effective. In particular, you might be using someone like Cloudflare because you need their denial of service protection, and caching is just turned on by default, so maybe you can just turn it off. But then again, some users might be accessing your site through an internal corporate proxy that has caching turned on. So you can never be 100% sure that your content isn't being cached somewhere. So the robust fix is to avoid unkeyed input, avoid taking input from HTTP headers and cookies as much as possible, especially on pages that might get cached. Now, obviously, you can avoid intentionally doing that, but you can't stop your framework from sneaking in support for these crazy headers. So you'll probably want to audit your application with a param miner in order to try and root out any unkeyed inputs that you might not be aware of. Once you find them, the ideal thing to do is to disable support for them completely, or to configure a reverse proxy in front to just strip those headers out. Or you could add them into your cache key, which effectively removes them from the cache poisoning attack surface. Now, what I've found is, more recently, is when people try to patch cache poisoning, things go wrong. So on this one website that I can't name because they haven't fixed it yet, someone said you've got cache poisoning, and they tried to fix it by asserting the request.host value is redacted.com. And they didn't realize that this exforwarded host header also populates the request.port value. So using that, we can trick the server into serving up a redirect to a port that doesn't exist, and basically permanently deny access to any page of our choice. Other times, even defensive measures that have nothing to do with cache poisoning will backfire. So here on Tesla's website, they have a web application firewall that blocks access to anyone who has the text burpcollaborator.net in any header, which I take as a personal insult. But the key thing is that when they serve up this 403, they don't set no cache headers on that. So that means I can send that request, and if I time it right, if anyone else tries to access the page on Tesla's new car, they get blocked. Also, even caching companies can get their mitigations wrong. So after I did my research last month, Cloudflare published a blog post saying how Cloudflare protects customers from cache poisoning. Now, first of all, I'd like to say good for them in trying to protect their customers. They're the only big cache that actually did technical measures, as far as I can tell. That said, it didn't go entirely smoothly. So they did two things. They updated their WAF to block all requests that have special characters in specific headers like exforwarded host. And they also updated their default cache key to add headers like exforwarded host into the cache key so that they can't be used for cache poisoning. So these are both fairly sensible measures. They don't prevent all cache poisoning, but they do prevent cache poisoning using certain headers. Or they would if I couldn't bypass them. So they've got this special feature. If the exforwarded host header matches the host header, they don't add it to the cache key. And that's fine. But there's a bit of a flaw with both these defenses. They only look at the first instance of each header. So if you send two headers, you can make the first one match the host header, and the WAF will think that looks absolutely wonderful, and the cache key will just be the normal cache key, but we can put whatever we like in the second header and get our cache poisoning working once again. I told Cloudflare about this yesterday. They're probably going to patch it fairly soon, so you might want to take advantage of it as fast as possible. Okay, that's pretty much it. You can grab the source code online. There's a white paper online, and as I mentioned, there's a cache poisoning challenge on my game if you want to get some practical experience with cache poisoning. Finally, the three key things to take away are header-based input is inherently dangerous, frameworks can hide lethal functionality, and cache poisoning is not theoretical. I'll take a few minutes of questions now if I have time. If you have any more after that, just come up and speak to me at the back or chuck me an email. Don't forget to follow me on Twitter. Thank you for listening.